Okay, so constant acceleration or uniform accelerated motion can be graphed in several ways. So we can see acceleration on a distance time graph. So say something was accelerating on a distance time graph. Let's start at 0, and it goes up, up, up. So this is accelerating. Slowing down. This, as it's leveling off, this is slowing down. Okay? Make that more level. Okay? Slowing down. If I'm accelerating, so speeding up, speeding up, I start at 0 again, and I go up like a J curve. So this is speeding up. I'm covering bigger distances in a smaller time, speeding up, so I'm accelerating. If I looked at something similar with, say, a velocity time graph, okay, so if I looked at something like this, this is a constant increase in velocity. That means, am I accelerating? If I'm keeping the same velocity, if I'm on cruise, am I accelerating? No. So in this graph, acceleration would be 0. Now keep in mind with our velocity time graph, yeah, but it's at a constant rate. Oh, you're right. Okay, erase this. I'm sorry, don't crucify me. Sorry, that was a note I made to myself, but I don't know. Okay, I apologize. Leave that. Okay? But, okay, let's keep in mind a few things here. For slope, we know slope is equal to delta y over delta x. So here, if I was going my slope, this is delta v over delta t. What is that?
Velocity over time.
Is acceleration. So if I find the slope of a velocity time graph, that's acceleration. Okay? If I find the area of velocity time graph, that's length times width, or I think that's equal to v times t. V times t is what? Okay? So an area of your velocity time graph, remember, is your distance or displacement. And we could also look at acceleration. If we had constant acceleration, it would just be a straight line. If we were to find the area of a velocity time graph, or an acceleration time graph, be length times width equals a times t. That's equal to my velocity. This, I remember why I screwed this one up. This should actually just be that this is uniform acceleration, not zero acceleration. Uniform acceleration. Thank you for asking about that. And that's what constant acceleration means too, right? Constant / uniform acceleration. So both of these things, so constant uniform acceleration, constant or uniform acceleration, this is the same thing happening represented on two different graphs. So we have constant acceleration on the VT graph, constant acceleration on the AT graph. It's the same, like the same thing is happening to the object, it's just represented on a different graph. Okay? Yeah? Okay, so let's look at a bit of an example. You okay? Dylan? Do you need to do a jumping jack or two?
I'm good.
Let's stand up and stretch, because Dylan needs to. I'm waiting! Stretch, over, up, Morgan's just watching Kim stretch. Not in a weird way. He was just standing there though, so I thought that was weird. Okay, let's take this graph and we're going to add a couple things to this graph, just to make it more exciting, okay? So, up here, add like a roller coaster swoop down, okay? And then put like a dot and do a swoop like that. Do you guys like roller coasters?
Yes.
I love roller coasters. Okay, let's label each of these kind of parts of the graph so that we can kind of discuss them more easily. So this slant coming up, let's call that A. What do you think we should call the slant, the horizontal line beside it? Lisa thinks we should call it C, but I say B. Okay, next, did you actually say that? I just kind of heard you, yeah, okay. She's teasing me. Okay, and then there's just, before it goes all the way swooping down, let's call the next slant D. And then the horizontal line over E. Swoop up is F. Swoop down is G. And last swoop is H. Okay, so let's analyze this a little bit together. So let's say object at rest. When is my object at rest? So this is displacement versus
J and object.
what? Oh, thanks. That's oh, goodness sakes, my life. Object. No. There we go. I don't know what just happened to my brain, but it's a good thing I'm not your English teacher. Okay, refocusing. I don't know what happened. just stopped working. Okay, when is something not moving on this graph? So no distance is covered.
B.
B, yes, I would agree. Section B, and there's another part where not, yeah, you guys, see, you guys are on it. I'm not.
Where's E?
Where's E?
The
The section that's, that's helpful, Evan. Oh dear. Okay. Now, let's say constant velocity in positive direction. Positive direction. So like in our forward motion. So where am I having constant velocity in a forward direction? A and C. So my velocity is staying the same. It's constant here and here. For note, which one is faster though? A or C?
C.
Okay, let's say that. But C is faster. Okay. Which one has a constant velocity in opposite? What are you guys giggling about? Well, then, I want to know. What's funny? Nothing? Okay. Constant velocity in the opposite direction. So now I say it turned around and went the other way, because the opposite direction will have a negative. So how do I tell if I've gone the other way in a DT graph? Yeah, so my D would definitely be okay. Let's say which one is accelerating in positive. I'm watching you, Lane. In positive direction. So acceleration in a positive direction. So it'll be like, it's not going to be a constant velocity, it's going to be accelerating. So it's going to look a little different than velocity. But yeah, F. Right? Because it's kind of swooping up. So I'm accelerating. I'm going faster. Okay? How about acceleration in negative direction? Ooh. Yes, I'm going to say in opposite direction. Or negative, yeah. Let's say opposite direction. So I'm accelerating in the opposite direction. G, yeah. Now, what if I decelerate? Accelerated. It sounds like something like celery or something. Decelerating. There we go. Okay. Decelerating in opposite direction. What's left? So I'm decelerating. So my curve has gone the other way. Beach. moving on. What? Bottom, the end of your notes. Oh, here it is. Okay, so now we're looking at a VT graph. Yeah, you tell us.
Trying to learn.
Okay. I keep smiling about something the grade 10s told me that Lane did this weekend. I already told him. The Spider-Man thing. It's so silly. Huh? Yeah, I know. Okay, so velocity time graph. Oh, let's focus. I'm not focused. Okay, let's do this. All right, so let's break this down into area chunks. So a triangle and a rectangle. These are the only ones I need to find out for the rest of the questions. So I'm just going to say this one is A2, this one is A1. You'll see why later. Okay, so let's analyze this graph. At what time does the object come to a stop? So no movement. What velocity would be what? 0, 6 seconds. So t is equal to 6 seconds. That's when our velocity is 0, because we're not moving. Does the object change its direction of motion? If so, at what time? Does it change its direction? If a velocity changed direction, what would its value be? Negative. So has it changed direction? No. Okay. At what time does the object slow down? From about, 3 to 4. So, or what did you say, X?
X
And Z, yeah. So sections X and Z. So we would think about this is like our negative acceleration. Because anytime it's slowing down, I have a negative acceleration. At what time is the object at constant velocity? Constant velocity.
Why?
Why? Very good. Oh, that's silly. So here, I'm not at 0. My velocity is at 20, but it's remaining at 20. So it's constant. It's uniform. It's the same. Okay? Calculate the acceleration at 3.5 seconds. So, acceleration means this is finding the slope, and it's a vector. So, let's scroll down and do that. Okay, so at 3.5 seconds, I need 2 points, because I'm going to find slope, so I need 2 points. So I'm going to label these points. If 3.5 seconds is right here, I'm going to use this point A and this point B. So your A and B. So point A is 350, the coordinates. And point B coordinates are 420. Slope we know is y2 minus y1 over x2 minus x1. So point B will be our x1 and our y1, and point A will be our x2, y2.
How do you tell what to label like X2, Y2, X1?
Like to determine which one is which?
Yeah.
I don't know.
How are we supposed to know?
Well, I'm going to find out for you. Okay, so 50 minus 20 meters per second divided by 3 minus 4 seconds. Is equal to negative 30 meters per second squared.
You get this in there.
Oh, you do?
It's like negative 30 over 1 instead of 30 over 100. That's all
Okay. So, Dylan, Lisa figured it out that it doesn't matter which one you choose as y1, y2, etc. You'll get the same answer. Which makes sense because you're figuring out the slope of that line. Right, okay, good. Thank you. Okay, so that's our A. If we were to put this, yeah, no, that's good. Okay, so our A meters per second squared. Hi.
All the 11s and the 12s. You're only missing 3, so I'm not really concerned. And these go to the youngest in the 11s and the 12s.
Okay.
Shouldn't it be in relation to where it is on the graph? Like third point comes first is y one. Like point
Yeah,
three.
I see what you're saying. I'm gonna still check about it. Mrs. Goodall will probably know.
I don't think it really matters.
You get the answer, it should angle it.
I just always thought.
So like in math, they let it
So I'll double check with Mrs. Goodall. Because there must be a rule. And those of us that like rules would probably just like to know. The rest of you're chill with it, so it's okay. Don't worry.
Not Dylan.
Not Dylan. Is that what you said? Not Dylan? I don't know. Never mind. Sorry. Okay. What is the distance traveled during the first 3 seconds? That's why we drew in that area thing at the beginning, was for the first 3 seconds. Because to find distance, that's the area of a VT graph, right? So area equals V times T, which is equal to D. And that's what I'm finding out.
No way.
Yeah, mind blow. Okay. But I have 2 areas, so I need to find, I need to add them both together. So I'm going to say my D is equal to A1 plus A2. So I think for A1 was my rectangle. So that's just 3 times by 10. And then my triangle is base times height divided by 2. So 3 times 40 divided by 2. 90 meters. And this actually asks us for distance, not displacement, so I don't have to have a direction. So, I should have, I'm going to just give you this little review thing for all of the graphs that we've done. And we'll do this before I stop class. Now. Okay. Evan, really?
Oh, I got skills I can't. I really thought you'd catch it.
Okay. Uniform motion. So if I was to just draw uniform motion in all of our graphs, I would have, that's not a straight line. You would have a straight line for your DT graph. So going the same velocity, uniform motion. If I'm going the same velocity, it would be a straight line across. So if I'm going the same velocity, I'm not accelerating, so acceleration would be 0. So that's all about uniform motion. That just means going the same v, okay? Same velocity. Now if I had uniform accelerated motion, so I'm actually accelerating, your DT graph has that curve to it. Uniform accelerated motion. Your VT graph will be a straight one because I'm accelerating but uniformly. Okay? Having a uniform acceleration, and my AT graph would be straight across. So now let's remind ourselves slope is equal to delta y over delta x. If I was to find the slope of a DT graph, that would be delta D over delta T. That would equal V. So my slope is V for my DT graph. Okay? If I was to find my slope of my delta V over delta T graph, that's A. So slope is equal to A. And I don't find slope of my AT graph. So now area, if I was to find out area, that's equal to length times width, or if it's a triangle, length times width divided by 2. I don't really have anything specific for my DT graph for area, but for area for my VT graph, area equals V times T. So that's equal, my area is D. If I was to find the area of my AT graph, that's equal to V. So this is kind of a cheat sheet to help summarize. What are the graphs all about? Okay, there were 2 types of motion that we covered in this chapter. Okay, the uniform motion and uniform accelerated motion. We're going to have one more lesson tomorrow, and then we'll be done this chapter. So these are the graphs that you need to be able to understand and interpret and find out these calculations, plus all of the extra calculations that we did from last class, and then doing your V equals DT graphs, or calculations.